Hi, this is the PV diagrams in thermodynamics problem solving part 1. I'm going to solve two thermodynamics homework problems in this and next video, and this is the easier of the two. So in this problem, you see a thermodynamic cycle sketched out in a PV diagram, starting from A, going to B, and then from B to C, and back from C to A. So as you are reading a question like this, the first thing I want you to do is read it carefully. It says an ideal gas expands isothermally. This is an important keyword. Along AB and does some amount of work. And then after part A, from B to C, it says that the gas then expands adiabatically along BC and does some work. So these are the two keywords that make this problem a lot easier than it might appear at first. So this is a first law of thermodynamics problem. So you are going to be using the first law at some point, so let me write it down. Change in the internal energy is equal to net heat transfer minus work done by the gas. And this is why the phrases isothermally and adiabatically make this question easy. It's because each of these two phrases make one term in the first law of thermodynamics equal to 0. When we say it's doing something isothermally, that means temperature is not changing, and since that's related to the internal energy, that means the change of internal energy for part A is equal to 0. Which means, looking back at the first law of thermodynamics, Q must be equal to W, since the change in internal energy is 0. So net heat flow into the gas must be equal to the amount of work being done, 730 joule. That's it. If it seems too simple, well, that's why you should read the question very carefully. This is actually a very simple question. All right, let's move on to the second part. So in part B, when it says adiabatically, it means exchange of heat is equal to 0. Once again, that makes our first law of thermodynamics equation very simple. With that, we can say change in the internal energy is equal to minus work done by gas. So this is what it means. Points A and B are on what we call an isotherm. It's what looks like 1 over x curve. And along this isotherm, the internal energy is constant. That's why we call it isotherm. Now, point C is on a different isotherm. And what we can quickly figure out from the information given in part B is that these two isotherms correspond to two sets of states that have energy difference of 440 joules. Amount of work done as the gas goes from point B to C. That's useful information to have, because then as the gas returns to A, we know the change of internal energy. Change of internal energy for this case is equal to 440 joule. It's the distance between the isotherms. It doesn't matter exactly from which point on one isotherm to which point you are going. The change in the energy is the same. And the question gives you the Q. So all we now have to do is solve for W in the first law of thermodynamics. The work done along this path is equal to Q minus delta E int. So for the numbers given, that would be 70 joules minus for 40 joule or minus 370 joules. And because this is negative work done, that's why it's saying work done on the gas. So they are expecting a positive answer. So you say 370 joules of work done on the gas as the gas moves from point C to A. Alright, that was fairly easy. We didn't have to do any difficulty integrals. As long as we were paying attention to what isothermal and adiabatic means and recognize that we are given enough information, especially using the first law. Now for part C, this is where a good understanding of what isothermal and adiabatic means is very useful. So it's asking, what type of thermodynamic process does the process CA represent? And if you somehow got into bad habit of seeing this curve, and curve means isothermal, then you're gonna get tricked the way I meant to trick you. Adiabatic curve is also a curve. Look at process B to C. It's a curve. It's not a straight line. One of the sections in chapter 3 covers them more thoroughly. So here, the best way to do it would be to rule it out one by one. So here's an argument I can make that it cannot be an isothermal process because points C and A are on two different isotherms. So if it's an isothermal process, it's going to follow an isothermal line. It doesn't, so it's not an isothermal process. Alright, then is it an adiabatic process? Well, we were given that there's some exchange of heat, so it's not adiabatic. So it's not an adiabatic process. Oh, that means it's neither isothermal nor adiabatic. Yeah, that's possible. A given thermodynamic process doesn't have to be any one of those four special named ones. It's just that those four special named ones, there are special constraints that make those particular processes easy to analyze. But this one happens to be one of those that's none of those. And since we figured that out, then it means there is enough information for determination that it is neither isothermal nor adiabatic. So that's it. That's this question. Once again, as long as you had a good conceptual understanding of what thermodynamics problem involves, you can do this very quickly without a lot of tedious calculations. So I'll see you for the second video. Until then, bye.